So we should know the techniques to solve the problem. For instance, if you are asked to solve this kind of problem, then you must use something. For instance, after changing it, you find the integrating factor like this one, and then after finding integrating factor, multiply, and then do something to solve the problem. So this is an analytic method. But in this course, we do not learn these kind of things. So in this sense, theoretically, the course is not very tough, theoretically. But then, what is the difficult thing? Computation. You should do the computation, meaning you should do coding or creating algorithms to solve the problem. So I heard this kind of comments many times. Oh, I understand everything, but I cannot program. This course doesn't cover very much. It doesn't even cover this level. So if you cannot code or if you cannot program, then course is meaningless, right? We solve the problems using computation or coding. So you should know how to code, or at least you should try to learn how to code. Because of this reason, I will use like 305 to 420 for code-related things for 2 weeks. So I will use this time to explain or answer questions about coding. And like 2 weeks, right? First and second week, I will spend time explaining basic things about coding. Of course, prerequisite itself requires coding techniques. Like CS something might be way harder than the coding required in this course. In any case, I will use 2 weeks from 3 o'clock to 4 o'clock to mention about coding or answer questions about coding. In addition, to check whether you really try to learn these kind of coding techniques, I assign some homework problems, and then later we will go to the syllabus and homework problems, and I will explain the reason. And let's briefly overview what we will cover in this course. First of all, we will learn about numbers and bits. We use numbers, and numbers can be represented by bits. And once bit representation is given, you can interpret it to create a number. So this thing is very, very important, and I will cover this extensively in the course. And during this time, I will focus on coding, right? You should code or program or create an algorithm to handle problems. And after this, I will briefly cover numerical techniques. So there are many techniques developed for numerical analysis. Because this course is not numerical analysis course, I will cover essential part of numerical techniques. For instance, what about bisection method? That kind of important thing. What about Newton's method? Those kind of important topics will be covered. Not the full numerical analysis, but like 20% essential part will be covered. And using these numerical techniques, we will initially try to handle ODE problems, ordinary differential equation problems, by computation. We do not do anything like this. We do not do analytic method like this. So to solve this problem analytically, you should know about this integrating factor, right? Without it, it's very difficult. So you should know these kind of things to solve problems. But when you use computation, the method is extremely easy. You don't have to understand these kind of things at all. We can use computational technique or coding to solve the problems. And afterwards, we will learn about the key area, partial differential equations. If we solve PDE problems analytically, it will be very, very difficult, right? Because it requires a lot of other things. Basic things like the separation of variables or using characteristics or something might be easy, but after that, you need to know a lot of difficult things. But if you use computation coding, PDE, ODE, or numerical or numbers are all the same. You can just code everything to solve the problem. In other words, you don't solve the problem by learning these kind of things. Computer solves it. The only thing that is required is your programming skill, right? You should program. Understand very minimal requirements, and then using minimal requirements, you program and solve the problem. For instance, when you have a differential equation like this, you must, if you want to solve this analytically, you must know about characteristics or something, and then collapse the variable and sort of things like this. And it's not easy, right? So after doing these things, you can solve the problem, and you can essentially get a function like this, right? Getting this kind of thing is easy, right? As I mentioned before. But if we use computational technique, you don't have to understand the method of deriving these kind of things after a lot of difficult steps. You don't have to understand these kind of steps at all. You just use computational programming skill to solve the problem. So essentially, PDE problem isn't any harder than multiplication problem. In other words, computation-wise, A times B isn't as easy as PDE problems or vice versa. PDE isn't as hard as multiplication. Difficult thing is programming, right? You should program or code the steps to solve the problem. Of course, minimal techniques will be covered. So after learning minimal requirements, you can program to solve the problem. And essentially, the idea is this. When you solve the PDE problems over this domain, then this is the input, and for each input point, we have the result represented by the height, right? Height above this plane, and then you determine these kind of points by your program. You don't do any analytic thing or doing special techniques. Just your computation or code will solve the problem. Then let's briefly browse the syllabus, and then I will let you know what you need to do and what you should remember. So let's briefly browse the stuffs. As you can see, there are 3 midterm exams on these days, right? On these days, 3 midterm exams. And I will post the sample problems on the web about the time of the exam. And after the exam, like 3 to 4 o'clock, I will do regular class. So you should not go home after finishing the exam. After the exam, after 10-minute break, I will resume, and then I will cover material and afterward. And final exam is a take-home exam, and you should submit your final exam by 4 p.m. May 11th. because homework or exam problems depend on coding, you cannot copy code from any place. If you copy code, automatically your grade will become F, immediately F. If you copy other codes or from the web or from the book, you will get an F. And we will cover these things, and then some people like books, and there are tons of books, but essentially these books cover the same thing, and in addition, there are very many nice web pages that you can use, very nice web pages. So I don't use a set textbook, but you can either buy these books or you can browse the website to find nice web pages. And as you can see, once you go to File section, you can find the summary describing these things, and you can print out these things and then study. But these are just brief summary, and you can find either, you can use Google search, or you can use some links to go there and then study deeper. And once problem sets are made, I will link those problems to these things, and I will open one homework example. This is the first homework. Very simple. Do A times B. That's it. Right? Do A times B. Then you may wonder, what is the question? In fact, I don't want to see the result of A times B. I want to check whether you can really program or want to learn how to program. Right? So A times B itself is not very difficult. Theoretically, I don't have to teach anything. You can develop all the nested things on your own, A times B. But I want you to really program or learn to program. So this is the first example, and later I will return back to this example and explain the requirements. So, for instance, someone may give this kind of thing, then I cannot give you any credit if you submit this kind of result. So I will show you. For instance, I programmed and then it calculates the result. So A times B is my program, and submit as the homework 1. And then you say, A is equal to anything, right? And then B is equal to anything. Then I programmed it. The answer is right, but I cannot give you any proof. Why? Because it's not you who programmed this thing. It's someone else, right? Someone else programmed it. Because of this reason, I imposed these conditions. I imposed the conditions like this, but for the details, I will use whiteboard to mention about requirements. So roughly, these are the things that we will cover in the course, and I will answer questions and then begin to cover bits and numbers. Bits and numbers are very essential, and because I don't know your level of understanding or coding skills, I want to be very slow about first 2 weeks. And in addition, from 3 to 4 o'clock every time for 2 weeks, I will cover coding related stuff. If you are very excellent in coding, you don't even have to be here. You can spend time on other things or stay here and ask other questions. So please ask anything, and then once I answer questions, I will begin to cover bits and numbers. Yes? No. You can use any language. In fact, I saw the answers written in Java, C, Visual Basic, and Maple Mathematica, MATLAB. Someone used Python, Perl, and Visual Basic application on Excel, something like that. And then I saw all the things. As far as you code, it doesn't matter. Of course, if I cannot compile or I cannot interpret, then I will ask you to give the interpretation or print out the hard copies, but it rarely happens. In some sense, the best tool might be MATLAB. MATLAB might be the best tool. Any other questions?
Well, are the midterms going to be coding too?
Coding will be questioned for first exam. Midterm, there are 3 midterm exams. First midterm exam will involve coding too. And the final exam also has coding.
You just write the code on paper?
Code on paper on exam 1, like pseudocode or code or algorithm or flow chart, anything.
It doesn't have to compile.
Right. I don't know to type them and then compile them. So, but coding will be questioned on the first exam, and then final exam is take home, and then there you will have coding problems. So as I mentioned, this course is a computation course. We don't learn any techniques like integrating factor or characteristics or something. We don't learn those kind of techniques. We just code everything, right, to solve the problems. Then let's begin. So I will be very slow, as I mentioned. Somehow, brilliant engineers or scientists found a method to distinguish on and off, or 1 and 0, or magnetized or demagnetized or something like that, right? So people can somehow distinguish this level and this level, right? So we call this level 0, we call this level 1, right? By magnetizing it or by some number of electrons or something, they say, oh, this isn't enough, then we call this 0. And if we have more electrons, then we may call it 1 or something like this, right? There are many, many different methods to implement 0 and 1. Somehow people know whether there is or there isn't, right? 1 and 0 concept is done. In other words, mathematical, especially numbers, right? Mathematical or especially numbers can be converted to bits. Bits means having 0 and 1, right? Converted to bits, and then vice versa, right? Bits can be interpreted this way. So, before considering this kind of conversion, I will focus on numbers. Our number system is positional number system. What does this mean? It means this. Assume that someone gives you this salary and someone gives you this salary. What would you take? You will take this salary, right? Why? Because it's positional. Position means something. Right? Position means something. Because of this reason, assume that you can distinguish bent or not bent of fingers. How many numbers can you count when you have these things? Without positional number system, you can know 9, right? 8 and so on, right? But with positional number system, how many can you count? Right, over 1,000 numbers we can count, right? So let's check it. 0, right? 1, right? 2, 3, 4, 5, 6, 7, 8, right? 9, 10, 11, right? 12, right? 13, 14, 15, 16. Positional number system is possible, right? 16, 32, right? And so on, right? So we can count the numbers this way. So with positional number system, we can count a lot. With 10 fingers, we can count 2 to the power of 10 or over 1,000 numbers. Any questions? Then, let's consider base. We use decimal representation means, we use decimal representations, and it means base is 10. Base is sometimes called radix, right? Base or radix is 10. So when you usually speak about some numbers, those numbers are in terms of decimal base. Then what does this mean? It means this. When you want to represent the number, we use 10 different digits, numbers, to represent one number. For instance, 0 can be used, 1 can be used, and then 9 can be used. So there are total 10 numbers, and using these 10 numbers, we represent one unit, right? And then one digit is represented, and the next digit, and so on. And then we use position to represent this. So mathematically, it's possible to use any base. Any base. In other words, assume that you have just 5 numbers. Assume that you have just 5 numbers, then using positional number system with 5 numbers, you can represent everything. So it is possible. Assume that human has just one hand. Then all the time, count this way, right? Then 5 numbers are enough to represent everything. Why do we study this thing? Because later we will limit ourselves to bits, right? Only using 2 numbers, we represent everything. Then, mathematical representation of this kind of number, right? 1, 2, 3 means this. 3, I will use ascending order. 3 times 10 to the power of 0, and 2 times 10 to the power of 1, and then 1 times 10 to the power of 2. Right? This is the meaning. Any questions or difficulties? Or sometimes people do not like ascending order, so let's write it in descending order. The same thing written differently. And later I will mention about general concept related to this kind of order called Indian, right? Called Indian. In any case, once we have a number, we know the meaning. Then assume that we have just 5 fingers. We have just one hand, right? Meaning 5 fingers. And then our number system has base 5 instead of 10. Then what does this mean? Because it's not decimal, when you use different number system, we usually write the base or radix, right? So it means not 123. It means 1, 2, 3 in positional number system with base 5. Then what does this mean? It means 1 times, instead of 10 to the power of 2, 5 to the power of 2. And instead of 2 times 10 to the power of 1, 5 to the power of 1. And then instead of this one, 5 to the power of 0. And it means, now in decimal system, so when you usually use numbers are written in decimal system, right? These are in decimal system. Here is not, right? This is not in decimal system, but here is in decimal system. Then it is 25 plus 10 plus 3 and 38, right? So 1, 2, 3 in decimal system is 123. 1 to 3 in the system with base 5 means 38. So I will be slow. If you have any questions or difficulties, ask me. Then I want you to interpret this thing. hexadecimal system. Hexadecimal system means there are 16 numbers. Then what does this mean? Please let me know the answer. Great, so let's write the result. So depending on your base or radix, the meaning of the number changes. The meaning of the number changes. Now, assume that we use base 2, in other words binary. Then how many numbers can you use to represent one digit? We assume that we have base 2, then how many numbers can you use to represent each digit? 0 and 1, right? 0 and 1, total 2 numbers we can use, right? So by just 0 and 1, we should represent the number. So what is this number with base 2? So I will write the answer. So 11, as you mentioned, right? So once we have a number representation, we can use those digits to represent any number. So essentially, any basic system can work, right? So depending on developments, some nations used like hexadecimal system, some nation used system with base 12, right? With base 12. Some used number with base 60, right? And so on. And in computer generation, because we can distinguish 1 from 0, binary representation is extremely important, right? So this is called binary representation. And this is called hexadecimal. And what do we call? I don't remember the names. So there are some names. But in any case, we can use given base system to represent numbers. In fact, in some set theory, we can do this kind of thing. We can remove 1/3 of the section, and then we do the same thing for each section, each subsection, right? When you handle this kind of thing, it's good to use base 3, right? If it's base 3, then we can match these kind of points using this representation. So depending on problems, we can choose our base. We should not be limited to decimal system. Especially when computer is involved, we can use any number system. Any questions? So I will show you the examples. For instance, when you use anything under base 10, we use the same numbers, right? The difference is this. It may not fill these things. It may stop somewhere, right? Assume that we have base 3. Then, after using 0 and 1 and 2, right? 0, 1, 2, we must return back to this number. We should use the next position, right? So when we use any base equal to or smaller than 10, then we can use numbers. But only if we have base 12, then we can use these numbers, 1, 2, 3, up to 9. Then what should we do? Because of this, in computer science, people decide to use alphabet to represent the number. For instance, A represents 10, and then B represents 11, right? Then, what does this mean? What does this mean in system with base 12? Thank you. 1 times 12 plus A times 10 to the power of, 12 to the power of 0, right? 12 to the power of 0. Then it is 12 plus A is 10, right? 10 and then 1, so it is 22. So in computer science or some hardware design, people use these things, and hexadecimal system requires total how many numbers to represent a digit? How many numbers are necessary to represent one digit? 16 numbers, right? Hexadecimal means base 16. Then 0, 1 up to 9, total 10 numbers, and then we need 6 more numbers, right? 6 more, so we use A, B, C, D, E, F. So this represents 10, this represents 11, this represents 12, and 13, 14, and 16 in decimal, right? When you don't specify, these are in terms of decimal system, right? Then, what about this thing? In hexadecimal system, right? In hexadecimal system, what is FF? It's correct, but I will show you why this is. So roughly, this is the reason. F times 16 to the power of 1 plus F times 16 to the power of 0. And F is 15, right, in decimal form. So 15 times 16, and then 15 times 1. So roughly 15 is the common factor. So it is 17 times 15. Then we multiply these things, then 255, right? So in computer programming, people use binary or hexadecimal system, or sometimes octal system. For instance, when you use Unix, you want to change the file permission type, then you say change mode, and then you use some numbers, right? 777 to let everybody use this 7. These are octal system, right? Octal system. You use 3 bits. 777 means, if we convert 7, then 7 means 7 in octal system means 111 in binary system. Do you follow me or not? Of course, I will mention about the conversion very soon. 7 in octal system is 7 in decimal system, right? And then 7 in decimal system is 111 in binary system. So 1 represents permit, 0 represents, right, impossible to access, right? So 111. So anybody can access these kind of files. So roughly, I mentioned about these things. And one more thing that I want to mention theoretically is floating point representation. For instance, you know 1.1. What is the meaning of 1.1? 1.1 means 1 times, I will use 11.11. This means 1 times 10 to the power of 1, and then 1 times 10 to the power of 0, and then this means 1 times 10 to the power of negative 1, and then this means 1 times 10 to the power of negative 2, or reciprocal. Then it means 111 plus 1 over 10, and then 1 over 100. Then it means 1111 over 100. So decimal, I don't even have to explain, right? Decimal system. But now the challenge is this one. Assume that this is given in binary system. In decimal representation, what is system?
Record 2.75.
Too fast. So I will let you know the meaning. It means what? 1 times 2 to the power of 1, 1 times 2 to the power of 0, and 1 times 2 to the power of negative 1, plus 1 times 2 to the power of negative 2. Then it means 2 plus 1 plus 1 half plus 1 quarter. So total 3 plus 3 quarter, right? So it is 3.75. So depending on radix, the meaning of this kind of number change, right? Any questions? Then, as you can see, I gave you an example doing the conversion, right? This is converted to decimal system, right? This number is converted to decimal representation. Can you do the reverse? It should be possible, right? It should be possible. So once this kind of number is given, you can represent in binary representation. So I will give you an example. So please find the number. You know the meaning of this, right? You know the meaning of this. So binary representation must use 0 or 1. And then? Someone found the solution. So when you usually represent a number, we convert every number to temporarily decimal number, and then using decimal calculation, we convert it back to some other numbers, right? So this is decimal representation, and then this means 1 plus 25 over 100, and then it means 1 plus 1 over 4, or 1 plus 1 times 2 to the power of negative 2. So we can match these things, and you can get this number. Then some of you might already detect this kind of difficult situation. In fact, it could happen to any base, right? From decimal to binary, or from binary to decimal. Always we can find the decimal representation of a binary number, because this is divided by 2, right? 10 is divided by 2, it's possible. In other words, we can have a number here, then we can represent the number using decimal representation. Exactly. What about the other way? Sometimes it's not possible, so I will give you an example. Assume that I gave you what is a good number? Yeah, even this might be challenging, right? Even this might be challenging. Can you find the binary representation of this number? So as I mentioned, from binary to decimal can be exactly done, right? But from decimal to binary may not be guaranteed. So in the real world situation, we don't have any guarantee of this kind of conversion. Then you should decide where to stop. In other words, you cannot write the numbers infinitely many times, right? You cannot write long numbers like this one, long numbers like this in your representation to convert it, right? It's not possible. So somehow you should cut, right? You should cut. There are two ways of cutting it. There are two ways of cutting the result. One is truncation, the other is round off. So assume that we have decimal number that doesn't have any stopping point like this. I will use famous number. Assume that you have this kind of thing. Then if you want to decide to use 2 digits after the floating point, right? After the floating point, if you want to use 2 digits, then you should cut at this point, right? At this point. If you ignore whatever it comes afterwards, then it's called truncation, right? But assume that you want to use 4 digits after the floating point, right? Assume that you want to use 4 digits after floating point. Then, as you can see, here, the next number is 9. 9 is closer to the number above this number, like 1, 6, or 9. If you use 9, take a look. Either 3.1415 or 3.1416 are the closest number using the 4 digits after floating point, right? Then, as you can see, 9 is closer to this number, to this one, so we can use this. Then it's called round off. And because of this, error happens, right? So these are sources of errors, right? So if you do this kind of calculations 1 million times, suddenly this error will propagate, accumulate, and then it creates big difference, right? So error happens because of this kind of conversion problem. And usually, people had hard time to round off when you have even base, right? Decimal itself even base. There are total 10 numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So usually, for instance, 8 is here, 8.0 is here, and then 8.9 is here, and then 9 is here, right? 9.0. So I will use number here. 8.0 is here, 9.0 is here. Then 8.5 is exactly the middle point, right? 8.5 is exactly the middle point, right? The distance between this, the two distances are the same. But people decide to include 5 to this group. So this is the decision. If people decided to include 5 to this point, it doesn't matter. Mathematically, no superiority or inferiority, right? As you can see, you can do either way, but people decide to round off this way, right? So if it's exactly the middle, we usually move it off. So roughly, these are the things that you already heard or used before. But we are covering this theoretic, and you will see these things in the future. Any questions up to this point? Then The next thing is real technical one. When people, conversion is not covered yet. So conversion can be done from any base to any base. So you may pick any base and then any base, and you may pick the base and base, then I will convert. So by doing it, by using an example, I will do the conversion. So please pick some number, not very big or long. So what number would you use? And what base do you want to use? 7, right? Then I want to convert this number to some number with base. You choose. What base do you want to use?
3.
3. So let's convert it, right? Let's convert it. Then the thing that you need to do is this one. You represent these things in decimal form, but in fact, if you can directly convert it to some number with base 3, then you don't need this step. But for explanation, I will use this anyway. So you convert this number first to decimal number. This isn't necessary in real programming, but I'm giving you this idea to explain the point. Any questions? So I'm using decimal representation to explain, but in programming you don't have to do it. Then 7 plus 2 plus 3 sevens plus 4 7 squared. And then 9 plus 49 is the common denominator, 21 plus 4, then 9 plus 25 over 49. Any questions up to this point? Then let's use base 3. So if we use base 3, we should represent these things using something times 3 to the power of something, and all following terms with this pattern, right? Following terms with this pattern. Then nine is 3 to the power of 2, right? 9 is 3 to the power of 2, so 1 times this one. And then, because 9 is all used, we don't have this thing or this thing. Any questions? And how many 1/3? 1/3 are there in this representation? About 1/2. This is about 1/2, right? How many 1/3? Well, just 1/3, right? Do you follow me or not? If you don't, then ask me. Then this become 1, 0, 0.1 and something, right? Something. Either truncate or round up. It's your decision, right? It's your decision. So I converted the given number with base 7 into a number with base 3. I will give you a task. Convert it to a number with base 2. And please let me know the result with 2 numbers after this decimal point, after this floating point, right? Calculate these 2 numbers with either truncation or round off. So once you are done, please let me know the result. So do you get this result? Or not? So I will show you the reason why. This 9 is 8 plus 1, right? 8 is 2 to the power of 3, right? 8 is 2 to the power of 3. And then 0 times 2 to the power of 2. 0 times 2 to the power of 1. And then 1 times 2 to the power of 0. And then 1 times 2 to the power of negative 1, and so on, right? So this is the result. If you have difficulties, ask. In fact, I even assigned the homework doing these things not by hand, but by programming. And someone made this GUI version. For instance, you use, for instance, decimal, you can write number, right? Then it can be written in binary form, or octal form, or hexadecimal form. So you can write the number in binary form, right? Assume that you decide to write a number in binary form, 1, 0. Then it can be written in hexadecimal form, or decimal form, or octal form, or binary form. It's very strange. I randomly chose these things. It's almost a miracle, right? Do you know the reason why it's a miracle? When I chose the number in that, oh, sorry. Yeah, I was confused. I thought it is the other way. I thought it was the other way. I thought I chose binary. Yeah, sorry. If it happened to binary and I chose some binary number, it became 1, it's a miracle. Do you follow me? So, in some sense, we used to use decimal, but it doesn't mean decimal is the best. No. In some sense, binary could be the best. So when you see some SF movies or something, you see a lot of 0 and 1s, right? A lot of zeros and 1s. Almost everything can be written this way, right? Your program, your data, your image information, almost everything can be written by 0 and 1s. Especially CD, DVD depends on 0 and 1. Then, in some sense, I cover these things because some of you have never seen these kinds of things before. Most of you might already master these things before, but some of you might never have seen these kind of things before. So I'm covering these things. And in fact, this is the real technical implementation that you should know. Of course, the others are important too, but this is the real technical one. When you use bits to represent an integer, especially unsigned integer, meaning 0 and positive integers, then it's straightforward conversion. In other words, assume that you have integer 7 and you want to use bits. Then you use, assume that you have this enough space, right? Then you should represent this number. Then you should use on, and off, right? So you can use these bits to represent integer. So in this sense, unsigned integer conversion is straightforward, right? 7 is written this way, right? 1, 1, 1, and then 0 up above, right? So it's straight conversion between decimal or some number and number in binary representation, right? When you handle unsigned numbers, there is no problem. There's no technical difficulties. Do you follow me? So unsigned number. Give me any unsigned decimal number, then I will convert it to binary numbers. Give me any unsigned number. So these are bits, right? These are bits. If you regard 0 as off and then regard 1 as on, then these are bits, right? So on, off, on, and so, right? So unsigned number handling isn't difficult. Then how can you handle signed numbers? Assume that you want to represent -7. Then how can you do it? So people considered a lot of different methods and how to use bits. And according to IEEE, people decide to follow these steps. Invert and add 1. This is it. So this gives us a negative number. So this gives us a negative number. Invert and add 1. What does invert mean? It means when you have on, right? When you have on, then it becomes off, right? And this is off, this is off. And this is off, then it's on. And this is off, then this is on. This is off, this is one, and so on. Right? So, and then add 1, right? Add 1. So if you add 1, then. So this is the representation of -7. So this is +7. This is -7. So please browse it and let me know. So extremely easy to implement negative number using bits. Invert and add 1. That's it. Why did people develop this way? I will let you know. It is like cyclic group idea. So assume that, because if it's too long, I cannot track down, I will use a space with 3 bits, right? This kind of space with 3 bits. Then with these 3 bits, how can I represent a number? First of all, this is 0, right? Nothing, right? 0, 0, 0. And then 1 is this. Two is what? This. And 3 is what? this, right? Of course, when you represent bits, you can use 0 and 1, right? So we call this 0, we call this 1, right? 0, 0, 0, 0, 0, 1, or 0, 1, 0. 0, 1, 0, those are not numbers. Those are bits, right? On and off bits. Then, what is minus 1? Invert and add 1, right? Minus 1 is what? Invert, then I should invert, and I should invert, and I should invert, right? So invert and add 1. So this is negative 1. And invert. If I invert, then on and on here, right? On and on here. And add 1. Then 1 is added here. Then it becomes this. What is minus 3? Invert this one. If I invert this one, it becomes this, right? I invert it, and then add 1. I have 4. Invert this thing, and then add 1. If I invert, then it happens, right? And add 1, then so I wrote down the chart, and please browse and ask questions. So as far as bits are concerned, this is it. With 3 bits, we can represent total 8 numbers, right? Total 8 numbers. As you can see, 4 and negative 4 are the same, right? 4 and negative 4 are the same as far as bit patterns are concerned, right? Then how can you interpret it? Should we call this 4 or negative 4? People decide to call this what? What is your choice? People decide to call this bit representation what? Negative. So negative is the winner. So if you have this, it's negative. So when you add 1 to this number, you get 1. When you add 1 to this number, you get 2. Add 1, you get 3. Add 1, you get negative 4. Add 1, negative 3. Add 1, negative 2. Add 1, negative 1. Add 1, 0. Add 1. So it's a cyclic group, right? So people develop numbers this way, especially IEEE. So in the past, when you program something using a loop, sometimes program languages allow like 2-byte integers. 2-byte integers, meaning 2 to the power of 16. Once it passes that kind of, half of that kind of number, suddenly it plunges to negative number. It really plunged to negative. So I will pause and then you can check. And in some sense, people want to call these sign bits, right? So once program checks the sign bits and then it detects ones here, then it automatically becomes negative. Because of this reason, even though mathematically these represent 4, the same 4, right? 4 and negative 4 are the same. We call this negative because in some sense we regard this as sign bit. So when you have these kind of sign bits on, then it is negative, right? Sign bits off, then it's positive. Positive or 0. So I want you to completely understand these things. If you have difficulties, ask me. If you don't, then I will assign some question with more bits than just 3 bits. Do you completely understand the idea? As you can see, if we create signed integers this way, by following IEEE suggestion, then we don't have to even create minus. We just make an adder, then the adder will do the job for both plus and minus. Right? Adding, right? Just adding it will do it. So always we are adding something. Then the task is this one. Assume that we have 8 bits. 8 bits are called 1 byte, right? 8 bits then represent 3 using 0 and 1. Instead of boxes, you use 0 and 1. Then what is it? If you use 0 and 1, then 3 is equal to what? 0, 0, 0, 0, 0. Any questions? This is it. Right? We can use 8 bits. So these are written in terms of 0 and 1s. Then what is negative 3? What is negative 3? This is my question. So this is negative 3, right? What happens if we add these things? What if we add these things? 1 and 1, right? 1 plus 1 is 0, right? And then we have carry over, right? 1. And 1 and 1. Always 1, no, and go to it. So it makes 0, 0, 0, 0, and then carry flag, right? 1. So as you can see, if we add negative 3 and 3, it becomes 0. Do you follow me? Bitwise operation, right? Bitwise operation. So let's make it small. Plus, right? This is 3 and negative 3, right? Do you follow me? Then if we add, then this becomes 0, right? 1 plus 1 is 10, right? 10. 1 is carried over, right? And 1 plus 1 is 0. And then 1 plus 1, 0, 0, 1 plus 1, 0, 0, and then carry, right? So carry flag. But as far as bits are concerned, the order filled with zeros. So negative 3 plus plus 3 is equal to 0. So it's like a cyclic group. In cyclic group, we group up, for instance, 5 numbers. 1, 0, 1, 2, 3, 4, and then next number is what? 0. So I will pause and then check whether you understand or not. Please ask questions if you have difficulty somewhere. What part?
I just don't understand how that works. I've never seen this before, so I don't know how you do that. How is 1 plus 1 0 and then
Oh, I see.
0?
I see.
1 is 0.
I see. Take a look. When we have 4 plus 6 in usual calculation, what happens? 4 plus 6 is 10. But 10 doesn't exist in our base system, right? So we use 0 and then carry over 1, right? The same thing. 1 plus 1 is binary system. That means we have only 2 numbers that we can use, 0 and 1. 1 plus 1 is 2. 2 doesn't exist in binary system. So we should use 0 and then carry over. Do you follow me? So in binary system, 1 plus 1 becomes 1, 0. And then that same thing happens to the next digit and next digit, and then it carries. Any other questions?
What happens to that 9th digit, basically? When you add those two, like we just did,
So,
one that you carry to
right.
we have 8 bits.
We have only 8 bits. We usually don't care about that kind of bits at all. Like that kind of bits at all. But in computer design, when that kind of thing happens, usually they store those values in flag forms. The register has storage area, bitwise storage area in each bit. They have something. So once you use debugger, you can see all the flags, carryover flag, all flags, other flags are there, and those are suddenly assigned, like it has flag 1 and 0. So once you use debugger, you will see the change, but you don't want to go there. Just in real design, you can design any way you want if that kind of thing happens. In other words, don't care about anything like this, right? Don't care about anything like this. Once it overflows, right, it goes above our limit, then don't care. In other words, we are handling just total 2 to the power of these numbers. For instance, 2 to the power 3 numbers, total 8 numbers in the previous case. In this number system, in this universe, there are total 8 numbers, right? In this universe, there are total 8 numbers. Beyond this number, we don't care. Do you follow me? If we add this thing and then somehow something happens, we don't care. We just care about these 8 numbers in this system. Similarly, if this kind of thing happens, it doesn't matter. Anything can be carried over above it, then we don't care. Just we focus on these 8 bits. Right? Our focus is on these 8 bits. Any other questions? But then one more problem, and then let's take a break. And then after this, I will mention about the possible implementation skills related to these things. And next time I will cover floating point representation, way harder than these things. But let's use 6 bits. 6-bit number will be considered. Then, for instance, pick any number, like 9, right? Then find the bits of 9 and negative 9. This is the task. And then afterwards, let's take a break. So let's meet 10 minutes later. By this clock, 3:05, let's meet. And I will mention about implementation skills. If you already completed on this implementation skills, you don't have to return. Then, as you can see the files, right? You can download this thing and save it, and then you can save the notes too. You can access the notes too. So, by now you cannot see it, but for instance, if you go to differential equations, of course, do not type my name, type your name. Then, as you can see the lecture and everything, and then download these things. Any questions about this archives? Then the next thing is homework. So, for instance, the first homework is very important. And as you can see, each hour you have 5% deduction. Someone already did. It should not take very long time, but you should do it. So take a look. This is the condition. You are multiplying 2 big numbers, but as you can see, we have this kind of periods, right? That means we cannot multiply big numbers like this. In other words, oh, A times B is A times B, and then maple does A times B and then give us the result. So you somehow break this up into 3 digits, and then 3 digits, and then multiply by maple, and then later cut. Then you don't get any point, right? What I don't want to see is this kind of thing, right? Because maple did this calculation. I want you to program to calculate this kind of thing. Because someone already did. I will show you how it runs. Do you see MATLAB somewhere? MATLAB.
Second row in the middle. Or
Middle.
second column, I mean, in the middle.
Thank you. Wow. Unfortunately, I cannot show this thing because it is archived. You can freeze and then copy this. So I will make it almost invisible so that nobody can just freeze it, and then even if you magnify, you may not be able to see. I don't know where those things are. Sorry. In any case, someone already did the programming. It is like within one page, and it calculates everything. And the condition is this one: you cannot multiply any number bigger than 3 digits. In other words, it's possible to multiply this thing. It's possible to multiply up to this level. 3 digits times 3 digits is possible, but anything above it is impossible. In other words, you cannot do it. You cannot do this. Then once you multiply 3 digits by 3 digits, then you will have 6 digits. Then you can break this up, right? The top 3 and then bottom 3. So roughly, this is my design idea, and as I mentioned, I'm not really giving you the code, but I'm giving you the idea. Initially, you should store numbers. You should store numbers in an array. And this array should have very big size, because in the past, I saw someone really name each element and then do the hard-wired calculation. So I was really shocked after seeing. So I increased the number of numbers in this representation. It should be at least 40 boxes, right? It should include 40 boxes. Then 40 boxes times 40 boxes means like 1,600 boxes, right? So it's impossible to hardwire this. So you should use array. In other words, this is A 0 or 1. You may use any array of your choice, right? This is A 2 and so you should program this way instead of saying A, B, C, D, E, and then hardwire everything. Similarly, B is equal to a number. And then this is B1 or B2 or something. You may name it any way you want, and I will let you know the basic skills later. After these things, you can create bigger number, right? This assume that this has this length, like n. Then you may pick bigger number, right? N plus alpha, some bigger storage area. And then you adjust, right? The last digit is adjusted, the first digit is adjusted, and then a few more carryover stuffs, right? You adjust more, right? So assume that this is C1, C2, and so on. Then carryover can be stored C0, C minus 1, or if it's not possible to use it, indices this way, then you may use different schemes. But I'm just giving you the idea. And then each time you multiply, where should it go? For instance, if I multiply first the smallest, right, numbers groups, then the result should occupy this and this area, right? Do you follow me? In your program, right? And if you multiply, for instance, this and this number, oh, I'm multiplying, sorry. I was confused between multiplication. So it's not just this much, it means 2n, right? I was confused between addition and multiplication. So you are multiplying, then 2n is still easy, right? So you have more numbers. So if you multiply these things, it comes here, right? And so on. So if you multiply these things, depending on this position, you should locate the result to some position like this, right? So you should do these kind of things. Of course, theoretically, it's not very difficult. It's not very difficult theoretical. But implementation is important. Then let's go back to the problem and then read conditions. But before going any further, I will briefly mention about the storing method. Storage should have this method. Assume that you want to store 1, 2, 3, 4, 5, 6, 7, 8 using 4 numbers, array of 4 numbers. Then this is possible. A0, A1 equals 1, 2. A2 equals 3, 4. A3 equals 5, 6. And then A4 equals 7, 8. Right? It's possible to store this way. Another way is this one. A1 equals 7, 8. A2 equals 5, 6. A3 equals 3, 4. A4 equals 1, 2. If we represent a number by using this kind of method, most significant number comes in the earliest assignment, then it is called big Indian. If you use the other way, then it's called little Indian. Microsoft follows little Indian. Microsoft follows little Indian, and some companies follow big Indian. I guess Sun Microsystem may follow big, I don't remember. But depending on computers, they follow big or little Indian. But you don't have to worry about these things. In your program, you choose whatever you want to use. Usually, little Indian might be very logical. Big Indian might be easy to interpret, but little Indian might be logical. For instance, once you want to look at a number, big Indian with 4 spaces or 4 slots, then you can just read the number directly. What is the number? By looking at 4 slots, you can read the number. 1, 2, 3, 4, 5, 6, 7, 8 is the number, right? If it's written in little Indian, then you should know the number of slots, and then you should assemble the number from the bottom, right? 1, 2, 3, 4, 5, 6, 7. It's a little tougher to interpret. But for other things, for logic or other things, little Indian might be a little bit helpful. So it is possible to use big Indian or little Indian in bit representation too. In bit representation, some computers use big Indian, some computers use little Indian. In other words, one can be written, assume that you have 3-bit computers, right? 4-bit might. So if you use little Indian, then this is the bit representation, right? If you use big Indian, then Oh, sorry. I should not. I should say this thing. So I will remove this thing and then mention, correct my mention. So assume that this is A1, right? A2, A3, A4. Then as you can see, the least significant digit is occupied by the number, right? And then 0, 0, 0. And then when you interpret, we interpret this way, right? This first, and then this one. So when you assemble, it becomes 0, 0, 0, 1. So this is little endian representation. If we interpret this way, right? If we interpret this way. But big endian representation is given this way. Then it is 0. It's just straightforward. As far as interpretation is concerned, big endian is more convenient. Because of this reason, some computers combine both. Something is interpreted in little endian, something is programmed in big endian, depending on. So do you completely follow the idea, right? So if our storage space is not enough, in other words, if we need to use more than one slots to represent one number, then there are two different methods, right? Little endian or big endian. So some computers use little endian bitwise, right? Some computers use big endian bitwise. So no mathematical difference, but practically, sometimes little endian is more convenient, sometimes big endian is more convenient. So mostly bitwise, big endian might be in some sense intuitional, right? In interpretation, or because we don't really do any calculation here, just using numbers. So when you program, you will encounter the same situation. Assume that you want to handle this number. Then how do you assign these things? If you assign A1 equal to this one, A2 equal to this one, A3 equals this one, then your assignment means big endian, right? Do you follow me? But if you don't assign this way, in other words, if you assign A1 is 7, 8, 9, A2 is 4, 5, 6, A3 is this one, then you decide to use little endian. Knowing or unknowing, you might use these things before, but now you have clear definition of big and little endian. Any questions about this endian? And as I mentioned before, logically, little endian might be superior, logically, especially when you use arrays or indices. Then little endian can be easily tracked down, but big endian, you should use different algorithm, a little bit harder, tougher to manage. You will see when you really program. So no questions about endian. Then one more, after watching the things, one more thing is, roughly one more thing will be enough, and then I will. You can use functions, built-in functions, as far as it doesn't, the functions do not, as far as the functions do not really multiply the numbers. Not big numbers, I mean. 3 digits is possible, but what does this mean? It means it's possible to use, for instance, floor function, right? Or Gauss function, or something, right? It's possible to these kinds of functions, because these functions do not directly multiply numbers. Why do we need floor functions? So roughly this is the idea. I have this number. After multiplying two numbers, I got this number. But I cannot store these things in one storage area. I should store this thing in the first storage and then I should store this thing in the second storage, or ice and I plus first storage area, right? I should store this in ice storage and then I plus first. When you really look at the number, it's not very difficult, right? But when we really use program, the program should store these numbers. Then how can you store this number here? How can you store this number here? Then use floor function. I don't know what floor function is in your programming language or software, but it's like this. 1, 2, 3, 4, 5, 6 divided by 1,000, right? And then truncate. This becomes, right? 1, 2, 3, 4, 5, 6. And then truncate, right? So you can use floor function, Gauss function, or truncate function to extract this number, right? After extracting this number, how can you extract this number? How can you extract this number? Just subtract this portion times 1,000 from this number, right? Do you follow me? Subtract this number times 1,000. This is okay. This is okay, right? Yeah. So this kind of thing is okay because it doesn't. So the goal is not allowing being multiplication doing the job, right? So this kind of thing is okay. So any questions then? As you can see, 1 to 3 can be extracted by truncate or floor or anything, and then the remaining portion can be extracted by this kind of thing. But there are better, sometimes even this is not necessary. Sometimes you may find some built-in function doing these things, then use it. It doesn't matter. So I will pause and then answer questions. If you don't have questions, then I will continue.
So we're allowed to multiply 3 numbers at a time?
Right, 3 number times 3 number is possible. Up to 1,000 is allowed, or up to 1,000, right? Because of this thing, right? Or if you don't want to multiply, then you shift, right? Shift. But there are better ways than these things, so you may find better ways. But these kind of small things are all allowed, right? Because it doesn't solve the problem. This doesn't multiply in numbers.
What does the Gauss function do?
Sometimes people call Gauss function like this. These are called Gauss function. So depending on your programming language, it may have floor function, it may have Gauss function, it may have truncate function, depending on your program. So you should not use all these things. You should use something that you may own, some built-in function.
So it takes the lowest integer.
Right. So any questions up to this point? Then a few more things and then return back to the problem set. So and one more thing is this one. So as I mentioned, I briefly mentioned it, but as I saw this kind of thing. Oh, someone programmed this way. A is 1, 2, 3. B is 4, 5, 6. C is 7, 8, 9. And then the other number. D is 1, 1, 1. E is 2, 2, 2. And then F is 3, 3, 3. And then I saw that A times D multiplied by or with A times D is stored in the result. Storage can be called like this. Right? Then as you can see, C times F should be stored in M and L, right? Do you follow me? And then B times F should be stored in K and L, right? Added, right? And then E times C should be add it to K and L. If you don't follow me, ask. And then B times E should be stored in J and K. Right? And then A times F should be stored in J and K, and similarly, right? So someone really hardwired everything. So I saw like pages of lines doing these things. And then the problem is this one is designed for only array of 3 numbers, right? Array of 3 number times 3 numbers. What if I ask you to multiply array of 4 numbers by 7 numbers? Right? So that's the reason why you cannot do these things. This is the worst thing. I saw this kind of thing before. Someone really writes down like almost 70 lines like this. So don't do it. Use array. If you use array, you don't have to do these things at all. And I will check whether other things that I can. And as I mentioned before, you can use anything, but the best thing is MATLAB. But Maple is good enough. Maple is good enough, and Mathematica is very nice. But these are not real programming languages. These can work, but you may use Java, C or C++, or Fortran, or assembly, or something. So you can use. I saw someone giving the result in Perl, Python. Then I will copy this this first homework, and then analyze individual each line.
And we're just supposed to make up any 2 arrays ourselves, or do you want it so you can input arrays?
I will use like array of 40 numbers or 60 numbers or something, right? And then run. If it runs, then I don't even have to look at the code. If it doesn't run, then I give you 0. So either way are you in. So I will analyze each line with you and then answer questions. First of all, as you can see, it is about 10 days from today, right? So you have more than enough time. Some students did it within about 1 or 2 days. Already submitted. But you have more than enough time to do it. And as I mentioned, because coding is essential, there is strict deduction. In other words, at 9 a.m., I will collect everything. If you submit something at 10:30, then 1 hour late, that means 5% off, right? Yeah, email. Or you can give me the CD or floppy disk, or you can come and then give. So anything, any method is okay. And task is very simple, right? Multiply 2 numbers. Very simple, right? Why? Because in the future, especially when you cover PDE problems, I cannot let you know about the coding. I should mention about the theoretical part, right? The requirement part. Then by abstract instruction, you should know how to create these kind of things, right? Algorithm or code. And as I mentioned before, the number is broken up this kind of way, right? You break off the number this way. Break up the number this way and then multiply them. And then as I mentioned, you may use big endian or little endian, right? A1, A2, or A1, A2, A3, A4, and so on, right? and then B1, B2, B3, and so on, right? So you
And are
multiply.
both supposed to be integers?
Right, integers. These are our integers.
Are they unsigned integers?
Right, signed integer is very easy to handle, but this the signed integer or unsigned is not the major concern here. The major concern is multiplying two big numbers, two big positive numbers, positive integers. Then the restriction is this, like you should not hardwire codes at all, right? You should not assign A1, A2, A3, hardwired A1, A2, or A, B, C, this stuff here, right? You should use arrays for A and B. This is the first. So I will check your result using these kind of big numbers, right? So I will multiply like 1,000 digit number by 1,000 digit number. In fact, later when you have time using FFT, I will ask you to multiply two numbers, right? So, what did I do? Maybe 0 create this problem, right? So even though it doesn't look very long, could this be over 300 digits? How can you know the number of digits mathematically? Thank you. Or log, right? Log. With base 10, right? I don't know the command well, so I don't have time, but at least, as you can see, Maple can multiply really big numbers. I even tried like 10,000 by 10,000 digit numbers. It's possible to multiply 10,000 by 10,000 digit numbers in Maple. In other words, someone did the programming. MATLAB cannot. MATLAB cannot. That's the reason why I want you to implement in MATLAB. So I will multiply these two numbers. So Maple can really multiply big numbers. MATLAB doesn't multiply. I will show you because we have MATLAB. So MATLAB cannot give you the exact result. Any questions? Then the second thing is this one. I just gave you an idea, but you should not follow this within endian direction. You can program it on your own, right? You can use little endian or something. And as you can see, when you represent a number, we break up the number using 3 digits, right? For instance, if you receive your paycheck may have like some number and then comma and something, right? So I use the same idea, right? So you can interpret this completely. And I said 3 digits possible, and then one more number is 1,000 multiplying is possible if you don't have other schemes, right? But if you have other schemes, you can find other schemes. So it's not possible to multiply like 1 million by 1 million, right? And you can use, this is the condition. Some built-in function or something may really multiply two big numbers, then I don't accept it, right? In other words, you should program that part, right? You should program that part. And roughly this is it. Array 1 and array 2 of size n, right? So 1, 2, 3, so total 40 numbers here, and each number has 3 digits, right? And then the array 3 should have 2 n digits, right? And then I will use a number with like 50 groups here, right? 50 sets here. And then I will check it. And you may ask why I ask you to multiply 2 numbers. Because I want to check whether you can really program, or you want to learn how to program, right? These are really required to solve harder problems. Later, I just ask you to do this, to do that, then you should do it, right? So I want to check whether you can, because for this thing, you don't need any theory, right? You know how to multiply 2 numbers, right? You don't need any theory. So I ask you these things, and then either you already have the skill, or you want to learn these kind of things, right? Or improve your coding skills. And you can use any built-in function, right? Any built-in function other than the thing that really multiply 2 numbers. And computer algebra systems, programming languages, software packages, anything. And roughly, I will give you the design idea. The design idea I already explained before, but roughly, I will use some shapes to represent the idea. So initially, you don't even have to develop, just you create 2 different arrays, right? 2 different arrays of numbers, right? First array, second array. And then you have answer array, right? Answer array with bigger size. And using loop, I loop, and then j loop, right? I running from 1 to n, j running from 1 to n. You multiply this number, and then all numbers follow here, right? All numbers. And then you locate the result to this and this place, right? And then next number, you locate number this and this place, right? And the next number, you locate. So you should program these kind of things on your own, right? So roughly doing these things, right? So you fill the result this way. And then do the same thing, right? But once you track down the correct position, it will not be very difficult, right? It will not be very difficult. So you add this kind of result each time, and then later you interpret. Now, of course, later, after covering fast Fourier transform, I will let you know the better methods to handle, for instance, 1 billion digit number multiplied by 1 billion digit numbers. If you use this kind of algorithm, then 1 billion times 1 billion loops are necessary, right? But if you use FFT, you don't have to do. But later, that will be covered later. Right now, let's focus on simple thing with simple idea. No special theory other than just this arrangement. Take a look. Theoretically, what is difficult? Theoretically. Assume that you are multiplying these 2 numbers, right? Then, depending on the location, you can almost double this position, or roughly this kind of area, right? You can locate the result. So roughly, what you need to do is using array, loops, and then some if conditions, and then breaking up the result into 2 different locations. So take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, right? And then 1, 1, 1, 2, 2, 2. So assume that we are multiplying these numbers. Then look, we have 5, that means total 10, right? 10 boxes, right? Then take a look. The result of this multiplication should be located here and here. Do you follow me? Is it difficult? Right? The result of this multiplication will be located here. You may pick two numbers here and here. What number do you want to pick here? I will locate it. What numbers do you want to multiply? And then like this, right? Then take a look. It should have 1, 2, 3, 4, 5 empty spots, right? At least 5 empty spots, right? For instance, for this we have 0 empty spots, right? For this we should have 1 empty spot. For this we have 2 empty spots, right? For this we have 3 empty spots, right? So we have these things then. 1, 2, 3, 4, 5 empty spots are necessary, right? And then the result should be located here. Do you follow me? Right? The result should be located after emptying 5 spots. And then, right?
How do you do this with
It is interpolation idea. Yeah, it takes some time, but I will let you know.
Convolution.
It is the interpolation idea, and we use functions. We invert numbers to functions, and then using the functions, we interpolate the result, and then so I will let you. I will even ask you to program. And then this thing means this location, right? This thing means these two locations. This thing means this thing. Do you follow me? So essentially, there is no theory, no hard theory involved, right? Just simple theory you can develop. So let's check it. This multiplication should be located here. This multiplication should be located here, right? This multiplication should be located here, right? And then this multiplication should be located here, and so on, right? This multiplication should be, and so on. So you can check where it should be located, and then after analyzing them, you should use array, right? You use indices, right? Indices to really locate the correct thing. So roughly, this program is nothing but doing multiplication and then locating, right? Locating means adding. It's essentially you fill in zeros here, right? You fill in zeros here, and then add and add and add and add. And if there is any carryover, then you just add that carryover to the following things. So assume that you have carryover situation, and then somehow your thing become here somehow becomes 1, 1, 2, 3. Then what should you do? You should not leave it this way, right? You should cut this and then carry it over to the next thing.
We have like in that second to the last, 3 numbers that might go in there. You'll have to add them, I guess. That might go over.
So addition of, at best, what happens is addition of 3 number and then 3 number. It can have 4 numbers in the result. It doesn't matter. That carryover can be handled in your algorithm. If it is over, for instance, 1,000 or 999, then, right? Something like that. So it's possible to add 3 digits and 3 digits, or even multiply 3 digits and 3. So please check whether you can really implement this or not. If you don't think it's possible, then ask me why you don't think it's possible. Or your question may help others. Of course, as I mentioned, this week and next week, I will have this kind of time one more time. So and even next time, you can ask more questions after trying these things. And then afterwards, there is no implementation-related lecture or discussion workshop. So please browse these things and ask questions. If you don't, then I will briefly mention about the homework problems other than just this thing, the next homework. So just simply, let me ask you, can you program this thing or not? If it's not, then let me know why. What part is difficult? Because there is nobody saying it's impossible. I mean, no, right? I will cover the next homework set. Next homework set is a little bit straightforward. It is 1 week after the first homework, and there are 3 homeworks like these to check whether you can really program or not. I will maybe use this page. So next homework is this one. It's simple function, simple function. So you should know how to create functions, right? You should know how to use branching. In other words, you should know how to use if condition. You should know how to loop, right? And then you should know how to use arrays and indices, right? And now, you should know how to create functions. And here, I ask you to create 10 different functions. For instance, with base D1 to decimal integer. In other words, like this. I don't have it here, but let me look at that binary to decimal. Binary to, can you find binary to decimal? Maybe decimal to binary. Second one? Right, this one. Oh, really? Yeah, so assume that D1 is 10, right? Assume that D1 is 10, then your input is 7, right? Your input is 7, and your output is 111, right? 111. Do you follow me? 111 in binary representation means 7, or vice versa, right? If you input 111, then you should get 7 if you want to solve problem number 1. And conversion from base 2 to base 7, right? From base 2 to base 7 conversion. So if you have 111 with base 2, then with base 7 conversion, it should be 10. Do you follow me or not? Right, so this kind of so a lot of functions a lot of conversions can be programmed. You should not create this kind of GUI program that I showed you, right? You don't need to do it, but I will use this kind of input to check your answer. In other words, I use input 7 and then or input 9, then your answer should be 1001, right? Input 9. If I use input 16, then your result should be 1000. So these things are necessary, and please browse these things and ask questions. As I mentioned, until next time, we will cover these 3 homework problems requiring coding skills. Questions? So I will go through each problem, but before going any further, I will let you know the requirement. You should not hardwire your code, right? In other words, your code may work for 3-digit numbers. No, your code should work for any digit number, right? In other words, I ask you to convert like 1,100,000, right? So 1,100,000 is given, right? Then with that input, you should get the result, right? So your code should not be limited by your hardwiring skill. And you may use numbers like 1 to 9, and then A, B, C, D, E, F to represent each digit, right? To represent each digit, you may use 0 to 9, and then A, B, C, D, E, F. Because our radix or base is under 17. All the numbers that you need are in these sets, right? In this set. In this set. And the next condition is this. It's already covered here. If you use base D1, then you may represent numbers using array, right? Like this. Because if you use 1, 1, 1, then computer may be confused, right? 1, 1, 1 is 111, right? So instead of using 1, 1, 1, you must use arrays, right? 1, 1, 1. In other words, if you want to represent this kind of number, 1, 2, 3, 4, 5, with base D1, then you should use array, right? 1, 2, 3, 4, 5, 6. Do you follow me? And the final, not necessarily final, but a few more. Yeah, bits. Bits, yes?
The numbers in that array can be greater than, if the base exceeds 10, you put in 11 or
We should use numbers. Each digit should not be greater than the base number. The base is the biggest number, but that base number cannot be used inside.
what if you have a base 20?
Oh, that's the reason why I limited it to D17, under 17.
Okay.
Everything is under 17. So 16 is the biggest number. 16 is the biggest base.
But the elements of that array are all integers. So if I want to represent a number.
Oh, I see. I know. I understand the situation. I see. Yeah, 10 is okay. 10, 11 is okay. Because you don't have to create one more if condition or conversion to change those 10 to A, or right, and then 11 to B. You don't have to do it. Just those numbers can be directly used. Then I will regard it correct. And as I mentioned, any built-in function replacing the coding of this will not be accepted, right? But other than these things, you can use any built-in. But any built-in function to this thing, then there is no point. And did I ask unsigned thing? Unsigned and then signed? Yeah, signed integer is number 6. You should follow IEEE standard, right? Invert and add 1, right? Number 6.
So what's that one we obviously can't pick an arbitrary large one. We need a maximum size on that one. How big can we go? Or how big do we have to go?
Like at least 40 different elements, right? 40 different elements I add. In other words, when you program, you can check the size of array. It's very easy to check the size of array by just one command, and then that is used in it. So in some sense, it should not have any limit, right?
40 bits then?
Yeah, at least.
The output is 40.
It's not fixed. You fixed 40 bits, but at least your program should handle 40 bits or more.
I guess in number 7, if I give this routine -1, I have to return an array of bits.
I see.
But
I see.
how many bits?
I see.
It depends on the word size.
I see. Yeah. So, for instance, you may fix it to like 8-bit, 16-bit, or something like that, and then you may give the input value like that, right? So if you have 16 bits, it's this way, or 17 bits. In other words, I give input, right, like 16 bits, then you should have 16 bit, 32 bits, or like 64 bit. And your program knows those things and then represent. Do you follow me or not?
How about the minimum number of bits?
40 bits.
Okay. Well, for number 7, can I write a routine that returns the minimum number of bits if needed?
The number of bits needed. I see. It means you just filling those top portion with zeros or truncating those unused. It will be excellent if you can implement that way. Right, it will be excellent. But because of signed bit, it's good to fix the number of bits. Like, for instance, so I will write the point. For instance, your program may require 2 input values, right? One is the number of bits, right? Like 40-bit number, or any number I can use, right? 16-bit number, 8-bit number, 32-bit number, or 40-bit number, right? And then, for instance, sign integer, right? And then -5, right? So this 40 represents 40 bits, and the -5 represents the number. Do you follow me?
Yeah.
Then your program should be designed this way. Then once you design this program, I run like this. 40 and then -5. Then your thing should show this kind of thing. 1, 1, 1, 1, 1, 1. Right? So your result should look like this, right? So this represents the number of bits required, right? And then this is the number that you need to convert. So there should be total 40 bits, right? Because of this, there should be 40 bits. Then your number is converted. The second one is, in some sense, automatic, because as the problem number 7, and problem number 6 is automatic. Yeah, 6 is automatic. 5, right? This is 5. This is 5, and then 6. You don't even have to do it, right? Your G already has fixed number of bits, right? Right, fixed number of bits, right? So you can directly convert it to a number. You see the difference between 5 and 6? 5 requires the number of bits designed by us, right? 6 itself already has fixed number of bits. So we don't have to assign the number of bits. Already bit number is there. Do you follow me or not? So I will write the reason. Take a look. 5. Integer 2 bits, right? Then, we don't know how many bits are you used. Because of this reason, we should include the number of bits, right? Number of bits, and then real integer, right? Then it occupies these many bits, right? These many bits. And then it converts it, right? It converts it to this kind of pattern, right? Do you follow me? But when you have these two integer, then already the number of bits cannot change, right? The number of bits cannot change, right? Then you can automatically find the number, right? 7. So for 3 weeks, you should intensively master your skills of programming, right? Creating algorithm, doing looping, making functions, and so on. These things are all required to solve hard problems. What is your tool to solve PD? These are your tools, right? Using these tools, you solve PD. So let's return back and then read the problems and ask questions. base
Arbitrary one.
arbitrary number, for instance, I may use base D1 equal to 2 or 10 or 3, then your program should know that and then run. So as I mentioned, these are not theoretically tough, but programming skill is required. But it's not that high level like CS1 something, right? CS1 something is way higher than this programming. It requires way more things than just the simple looping, branching, or function creation.
In the problems that require a floating point, you said use the IEEE.
That will be mentioned the next time. I didn't even cover the theory of that thing, but after covering it, I will.
Right, but that's what we're supposed to use the IEEE standard for.
IEEE standard for add, the invert and add one. That is required here for integer handling, signed integer handling.
Right, but what about the ones that are the floating point?
Oh, we don't handle floating point here. Or integers here.
What about real number?
Yeah, real number.
Does that mean integer then? Number 8, 9, 8, 9, and 10.
Oh, I see. These are not IEEE, just conversion. This is a little bit, I will explain. Good question. This is doing, sorry. Good question. So, these are not IEEEs. These are just your function converting, for instance. So I show you just doing this thing, this kind of thing with right? Doing this kind of thing to this kind, right? So it's not IEEE style. It is just doing the conversion. Do you follow me or not?
So presumably your inputs are strings or
Array or something with.
if it's an array, how do you specify what the decimal point is?
So it's good to specify this way.
Oh, when we're converting it to another floating point number in a different base.
So then give the number of the base. Give 1, 1, 1, 1, 1, comma 2.
Right? So 1.11 can be represented by 2, right? By 2 arrays, right? So 2 arrays, 1, 1 and 1, 1. And then the result should include 0, 0, 3 or just 3 and then 7, 5. So this portion represents the point before this floating point. And then this point represents the digits after the floating point. And then the result should be designed the same way. Like this represents the point and then after. Good question.
Presumably we need an input to specify the base as well.
Right. So for instance, conversion like this, 2 to 7, right? 2 to 7, converting 2 to 7. And then this number, so we need 4 input values, right? 4 input values, including array. So for instance, to create this kind of function, I may write it this way: convert 2 to 10, and then 1, 1, 1, 1. But you can design anyway, and then the result should look like right? The result should look like this, right? Or double array or anything.
Would it be okay to just use a string to make it easier?
And it doesn't matter. Yeah? String is okay too. But string means you should use conversion. I don't require you to do higher level things, but at least as far as it does this kind of function, then it's okay. So please browse the problems and ask questions. Of course, you have one more week to ask questions for homework 1 and 2. But after doing these 3 homeworks, you will be very confident in your programming skills. And afterwards, once I describe something in abstract form, then you can really program to run. So please browse the problems and ask questions.
Again, on 8 and 9, when we're doing a real number, obviously it might be something that just doesn't come out neatly in our other base.
Then you do truncation or round off.
We get to pick where we want to truncate or does that-
Right. Anywhere you can truncate, like 3 digits or 4 digits. Or you can give an option. So function can be created flexibly, right? Sometimes you fix it, or you can let users to choose it, right?
If we were to use this is just kind of a question for future reference too. If I, say for example, did want to write a GUI for this, would it, since that's not handling any of the computational end of stuff, could I just, pull stuff in from the Windows API or something to do the GUI?
Yeah, yeah.
I'm probably not going to. I just wanted to know for future reference.
In fact, if I have enough time, I want to make a converter doing all of these things in one GUI, but I don't know whether I may have time forever. So if you have no questions about this, I will show you homework 3. But unfortunately, homework 3, theory was not covered, but at least I will explain it, save it, and then go to that. So there are 3 functions that you need to create here. So, 3 things: real numbers to bits, and then bits to real numbers, and then calculating the boundary, maximum and minimum numbers that we can represent. So for instance, assume that you have bits like this. Then how can you implement this kind of number? That kind of thing will be mentioned next time. Of course, you can design anyway, but I will let you know IEEE style. That one is the standard. And then that kind of thing will be mentioned. So 3. So without theory, you cannot even imagine. So the one asked on homework 2 has nothing to do with this IEEE style. Just bitwise convergence, straightforward thing, and IEEE style will be mentioned next time. So let's stop here, and you may approach to ask questions.